You wake up tomorrow, you step outside, and the sky is wrong. A pale stone river cuts the heavens in half, horizon to horizon lines brighter than the moon, casting shadows on the ground at midnight. Where are you? According to 500 million-year-old evidence buried in limestone, you might be standing on Earth. Let's start with what nobody ever asks first, but should. Not did Earth have rings? Not what caused them? Not when did they vanish? The first question should be, what would it have actually been like to stand underneath them? Because if we don't feel this, if we don't inhabit this world, then the science that comes later is just data. And data doesn't keep people watching. Wonder does, so close your eyes for a moment, then open them, and be standing on a beach somewhere in the mid-latitudes of ancient Earth. The water is warm, the sky is clear, the sun is setting, and as darkness falls something rises. These are not Saturn's rings. Not icy, mirror bright and blinding. Earth sits too close to the sun for ice to survive in orbit. The rings you are standing under are made of silicate-rich rock, essentially ground-up stony asteroid material. Rock doesn't sparkle. It absorbs light, scatters it poorly, holds it dimly. So what you see is a pale, dusty band, like a smeared Milky Way drawn with chalk on dark glass. But dim does not mean undramatic. The experience of these rings changes completely depending on where you're standing. At the equator, you see no ring at all, just a razor-thin line slicing the sky from one horizon to the other. The rings seem perfectly edge-on, like someone drew a single chalk stroke across the heavens. Move 20 degrees away in either direction, and the ring opens up into a towering, dusty arch, a massive curved structure dominating a significant portion of the sky above you. Around 40 degrees latitude, the effect is at its most theatrical, a vast elongated band, like a rainbow of stone stretching clearer across the sky, from horizon to horizon, its far ends cut off by the curve of the Earth below. A cosmic bridge whose feet disappear into the ground. Near the poles, the ring barely appears at all, a faint glow hunched at the horizon, like a permanent twilight that never quite rises and never fully sets. At night, the rules of darkness break. In the mid-latitudes, dust in the rings scatters sunlight from Earth's day side back onto the night side. This is called ring shine, and it means that true darkness simply doesn't exist. The rings glow brighter than the moon. The moon itself shrinks into irrelevance, a small disk lost in a stone halo. Entire civilizations could have lived their entire existence without ever once experiencing a truly dark night sky. But you never see a complete ring. Earth's shadow cuts through it, a fat black arc curving across the glowing band as the planet rotates, carving a dark bite out of the arch that sweeps and shifts through the night. Like a lunar eclipse, except it's the ring being eclipsed. Every single night. It sounds like the establishing shot of a science fiction film. It is not. It is what scientists now think our sky may have genuinely looked like. And the clues that prove it are hidden in places nobody thought to look. Now we need to go back. Not 466 million years yet. First, we need to understand what made a team of geologists in Melbourne, Australia, in 2024, look up from a stack of ancient limestone and say, wait, this shouldn't be here. Ordovician limestone is found all over the world, in Sweden, China, North America, Australia, across dozens of countries. It formed on the floors of shallow Ordovician seas, building up slowly over tens of millions of years, one thin layer at a time. And buried inside almost all of it from roughly 466 million years ago is the same strange anomaly, an enormous global spike in L-chondrite material. L-chondrites are a specific family of stony meteorites, small, dense, chemically distinct. You can identify L-chondrite material in rock because it carries a signature set of elements that essentially shout, "I came from space." The background rate of this material in sediments is consistent and low. It reflects the steady, quiet trickle of space dust and occasional small meteorites that Earth receives every year. The background hum of the solar system. But at the Ordovician marker, at 466 million years ago, that trickle becomes a flood, a factor of 100 to 1,000 times the normal background rate, worldwide, sustained for approximately 40 million years. For tens of millions of years, the Ordovician skies blazed with shooting stars, not as an occasional event, not as a week-long shower. Constant. For 40 million years, rock from space rained down on Earth, leaving its chemical fingerprint in limestone from every continent. Something happened. Something sent a colossal amount of L-chondrite material raining onto our planet, and whatever it was, it lasted longer than some species survive. The obvious explanation was always, a large collision in the asteroid belt broke apart an L-chondrite parent body. Fragments drifted inward, Earth got peppered. Neat, simple, sensible. Until 2024, when a team looked at where the craters actually are. Professor Andy Tompkins at Monash University in Melbourne led a team that asked what sounds like an obvious question. If all these L-chondrite meteorites fell from broken up asteroid belt debris, scattered randomly through the inner solar system, then the craters they left should be scattered randomly across Earth's surface. Should be. Tompkins gathered every confirmed or well-documented impact crater from the Ordovician bombardment period that was large enough to be preserved over 500 million years. He came up with 21 craters, spread across modern-day Europe, North America, Australia, and parts of Asia. Then he did something clever. Continents move, plates shift. Over 466 million years, Australia has migrated, Europe has drifted, North America has rotated. Today's geography is absolutely nothing like the Ordovician geography. So Tompkins used tectonic plate reconstruction models to run the planet in reverse, to peel back the continental drift and put every crater back where it actually formed, in Ordovician coordinates. When the reconstruction was complete, the team looked at the result. All 21 craters fell within 30 degrees of the Ordovician equator. Every single one. Not most of them. Not a cluster with a few outliers, all of them. Packed into a narrow equatorial band. Even though more than 70% of Earth's crater-preserving crust at that time lay outside that band. There was plenty of ancient land elsewhere. If impacts were random, plenty of craters should have formed there too. None did. Tompkins ran the statistics. The probability that 21 random asteroid impacts would all land within that equatorial strip by pure chance, 1 in 25 million. To put that in context, you are roughly twice as likely to be struck by lightning twice in the same year as you are to get this crater distribution by accident. Something was guiding those rocks. Something above the equator. Something in orbit. At this point, the old explanation doesn't just look weak, it looks wrong. Here's the fatal problem. If a large L-chondrite parent body shattered somewhere in the asteroid belt, its fragments would spray inward, through the solar system in all directions. Earth would certainly get hit, but so would our neighbors. Mars sits closer to the belt than we do. Any debris wave heading inward should have struck Mars more frequently and more violently than it struck Earth. The Moon has no atmosphere to protect it. Its surface is essentially a permanent historical record of everything that has ever hit the solar system. Every impact spike, every bombardment event, every rocky catastrophe. If something shattered in the belt and peppered the inner solar system, the Moon should show a clear crater spike too. Researchers looked. Mars matching spike around 466 million years ago. Moon, no matching spike. Earth shows 40 million years of L-chondrite bombardment. Its nearest neighbors show nothing. The debris cannot have come from a random asteroid belt breakup, because a random belt breakup would not aim itself exclusively at Earth while ignoring Mars and the Moon at the same time. The source has to be local, close enough to Earth that its debris stayed near Earth, too close to Mars and the Moon to affect them. There is only one kind of source that fits that description: material in Earth's own orbit, and there is only one event that could have put that much L-chondrite material into Earth's orbit in the first place. Here is what Tompkins and his team believe happened on a specific day approximately 466 million years ago. A large asteroid, roughly 10 kilometers across, crossed paths with Earth. Not a collision. Something in some ways more terrifying, a near miss. It approached on a trajectory that brought it inside what physics calls the Roche limit, the critical distance within which a planet's tidal forces overpower the internal self-gravity holding a smaller body together. Here's what that means in practice. Gravity is not uniform. The side of an approaching asteroid that faces Earth feels a stronger gravitational pull than the side facing away. As the asteroid gets closer, that difference grows. At some distance, the Roche limit, the difference across the asteroid's body is so large that the tidal force exceeds the asteroid's own gravity. The rock loses the tug-of-war. For a rigid, solid, rocky asteroid near Earth, the Roche limit sits roughly a few thousand kilometers above the surface. For a loosely bound rubble pile, chunks of rock held together by gravity rather than structural strength, it's closer to 15,000 kilometers. Our 10-kilometer asteroid passed through that zone. It was torn apart, not violently, as in a collision, but gradually, as tidal forces found every weakness, every fracture, every joint, and pulled the body apart from the inside out, piece by piece, layer by layer, until what had entered the Roche limit as one rock left it as a swarm of hundreds of thousands of fragments. Most of those fragments were now moving on trajectories that kept them inside Earth's gravitational sphere of influence, the Hill sphere, where Earth's gravity dominates over the Sun's. They were trapped, in orbit. The debris didn't immediately form a neat flat ring. At first, the fragments followed wild elliptical, chaotic paths tilted at all angles, some skimming close to Earth, others arcing far outward. Then they started hitting each other. Step 1. Collisional damping. Every collision between two fragments exchanges momentum and bleeds off energy. Elliptical orbits become slightly less elliptical. Random inclinations average out towards something more uniform. Over thousands and then millions of collisions, the wild swarm gradually circularizes and flattens. Step 2. Equatorial alignment. Earth is not a perfect sphere. It has an equatorial bulge, a slight flattening at the poles and a widening at the equator, making the equatorial diameter about 43 kilometers wider than the polar diameter. This asymmetry creates a slightly uneven gravitational field around Earth that exerts a slow, steady torque on orbiting objects at an angle, like a gyroscope that wobbles but eventually settles. Inclined orbits are gradually nudged toward alignment with Earth's equatorial plane. Step 3. The Roche limit locks it in. Inside the Roche limit, any clump of fragments that starts to gravitationally attract its neighbors gets torn apart by tides before it can consolidate into a proper moon. The debris cannot build itself into a single body. It is locked permanently into being a ring. The result: within a timescale of tens of thousands of years, the chaotic swarm settles into a flat equatorial disk of rocky debris orbiting Earth above the Roche limit. A ring, not icy and glittering, rocky and pale and dusty. Here's the thing you need to understand. Earth is not special in this story. Rocky planets grow and lose rings. It is not a one-time event for a one-time world. It is a recurring cycle written into the mechanics of gravity and tidal forces. We know this because we have watched it playing out, in slow motion, at Mars. In 2017, researchers Andrew Hesselbrock and David Minton modeled the orbital future of Mars's inner moon, Phobos. Phobos is already spiraling inward toward Mars due to tidal interactions. In approximately 70 million years, it will cross inside Mars's Roche limit and be torn apart, forming a ring around the red planet. That ring will slowly drain as material rains back onto Mars, but the remaining material outside the Roche limit will eventually clump into a new, smaller moon, which will begin spiraling inward, which will eventually form a new ring. Ring becomes moon, moon spirals in, moon becomes ring again. Their models suggested Mars may have gone through this cycle 3 to 7 times in its history, and that both Phobos and Deimos themselves might be the leftover product of previous moons that formed from earlier ring systems. Even more telling, in 2020, separate research confirmed that Deimos's unusually tilted orbit can only be explained if Mars had a ring system sometime in the deep past, a ring that pushed Deimos outward and left this orbital signature embedded in its path like a fossil. Mars carries the evidence of its rings the same way Earth might carry its evidence in Ordovician limestone. And then there's our moon. The leading theory for how Earth's moon formed involves a Mars-sized object called Theia slamming into the proto-Earth roughly 4.5 billion years ago. The impact sprayed material into orbit, a temporary ring-like disk. Collisional damping, and the equatorial bulge circularized and flattened it. Over millions of years, clumps outside the Roche limit coalesced into what became the Moon. Earth's moon may itself be the end product of Earth's first ring system. If it happened once 4.5 billion years ago, and if the pattern at Mars repeats, there is nothing fundamental that prevents it from happening again. And Tompkins is explicit about this. This wasn't the first time Earth had a ring, and it won't be the last. Let's be honest about something. The romanticized image of a ring glowing overhead at dusk, casting beautiful ring shine across the night sea, is not the full story of what a rocky Earth ring actually meant. From the ground of Ordovician Earth, the ring's decay would have been a lived reality. The sky was literally falling. Here's how. Any ring that forms below Earth's synchronous orbit altitude, roughly 35,800 kilometers, orbits faster than Earth rotates. That creates a tidal interaction between the planet and the ring that steadily bleeds orbital energy from the ring and transfers it back into Earth's spin. Every orbit, the ring loses a tiny amount of energy. Every orbit, it drops fractionally lower. Every orbit, dragged from the outermost layer of Earth's atmosphere, the wispy, tenuous exosphere, extending from roughly 700 to 10,000 kilometers, the fragments down just a whisper more. Over thousands of orbits, tens of thousands, those whispers become a sentence. You are falling. From the surface, this manifests as a constant, relentless rain of space material. Most of it arrives as dust, invisible except as a long-term chemical enrichment of sediment layers. The L. chondrite signature in Ordovician limestone worldwide is, in part, the chemical record of ring particles dissolving into the atmosphere and drifting down. But occasionally, regularly, even something larger deorbits. Fragments tens of meters across light up the sky as brilliant fireballs, arcing steeply downward, brightening to impossible intensity as they hit thicker atmosphere, and exploding or slamming into the ground somewhere near the equator. This is what leaves craters, not random rain from the asteroid belt, not a chance strike from an errant rock, a systematic, geometry-constrained equatorial bombardment from a collapsing ring directly above. Which is exactly the pattern Tompkins found. The Sun adds another mechanism. Charged particles from the solar wind bombard ring material, stripping electrons off dust grains. These charged particles then follow Earth's magnetic field lines down toward the poles and equatorial regions, as they finally collide with the upper atmosphere. The result, a faint, ghostly curtain of light glowing in the high-altitude sky. Not the vivid green and magenta of modern auroras, but a dim, widespread luminescence along the ring's equatorial path. Beautiful, and a slow particle-by-particle dissolution of the ring itself. Then there is our own moon, patiently undoing the ring with every orbit. As the moon passes overhead, its gravity tugs on ring particles at different strengths depending on their orbital position. For certain particles at certain distances, these tugs repeat at the same orbital point, a resonance. Small repeated kicks from the moon's gravity destabilize those particles, nudging some inward toward Earth and ejecting others outward toward escape. Over millions of years, these resonances carve gaps through the ring, accelerating the whole structure's collapse. Put all three mechanisms together, tidal decay plus atmospheric drag, plus lunar resonances plus solar wind erosion, and the ring's lifetime is roughly 40 million years, which is exactly how long the Ordovician L. chondrite spike lasts. The ring's predicted lifetime matches its observed geological signature down to the tens of millions of years. But the ring didn't just leave craters and chemical signatures in limestone. According to Tompkins and his colleagues, it may have done something far worse. It may have turned down the sun. Near the end of the Ordovician period, roughly 445 to 444 million years ago, Earth underwent one of the most severe cooling events in its history. Geologists call it the Hernantian glaciation, a rapid temperature drop of approximately 8 to 10 degrees Celsius that turned much of the southern supercontinent Gondwana into a colossal ice cap. The consequences were catastrophic. The Hernantian glaciation triggered the late Ordovician mass extinction, the second largest mass extinction event in Earth's history. Approximately 85% of all marine species were wiped out. Entire ecosystems that had been complexifying for tens of millions of years were simply erased. For decades, the standard explanation for this ice age has been the El Chondrite dust influx might have reflected extra sunlight or seeded extra cloud formation, a cool down by space dust. Tompkins proposes something more direct and more powerful, a ring casting a planetary shadow. Here is how it works. Earth's axis is tilted roughly 23.5 degrees to its orbital plane. As Earth orbits the Sun, different hemispheres tilt toward and away from the Sun through the year, creating seasons. During our ring's presence, that tilted orbit means different parts of the ring's shadow sweep across different latitudes through the year. June through August, Earth's northern hemisphere tilts toward the Sun. The ring's equatorial shadow falls predominantly over southern tropical latitudes, making southern winters harsher and longer. December through February, the northern hemisphere tilts away. The shadow shifts north, deepening northern winters. At the equinoxes, when neither hemisphere tilts toward the Sun, the shadow falls as a concentrated band directly on the equator, briefly but significantly dimming the most solar energy-rich strip of the planet. Even a modest reduction of 1–2 degrees Celsius in average temperatures at tropical and subtropical latitudes can shift storm track patterns, altering where precipitation falls, disrupt ocean circulation, changing which parts of the deep ocean upwell cold. Nutrient-rich water, sea level changes as glaciers grow, and water is locked up as ice-stress marine ecosystems that evolved under consistent solar input and Gondwana. The southern supercontinent, where most of Earth's land was clustered, sat at exactly the latitude where harsher winters would allow ice to accumulate without fully melting in summer. Just enough extra cold, just enough extra shadow. The runaway growth began, glaciers crept outward, the ice cap thickened, sea levels fell, marine habitats that required shallow coastal seas vanished, and 85% of the species living in those seas went with them. A single asteroid that didn't quite hit us, a ring that formed from its remains, a shadow that dimmed the tropics, an ice age that killed most of life in the ocean. All connected, all from one near miss 466 million years ago. Let's come back to the present. Let's say, hypothetically, that tomorrow a near-miss asteroid threads inside Earth's Roche limit and deposits a ring in orbit. Same as before, same mechanics, same debris. What changes? At mid-latitudes, London, New York, Karachi, Sao Paulo, you would never see a truly dark night again. Ring shine would wash the sky with a permanent dusty glow brighter than the full moon. You'd still see the brightest stars, you'd still see planets, but the texture of the night sky, that familiar inky darkness, would be gone, permanently replaced by a pale stone halo. Most people would find it extraordinary, breathtaking, the kind of sky that would immediately become the defining visual of the entire era. For the first few months, then the practical reality would set in. Satellites in low Earth orbit travel at approximately 28,000 kilometers an hour. At that speed, a collision with a grain of sand deposits the energy of a small explosive. A collision with a fist-sized rock ends a spacecraft's operational life instantly. A ring full of rocky debris in the same altitude band as our satellite infrastructure would be catastrophic. Every satellite, GPS, weather, communications, military reconnaissance, internet constellations, Earth observation platforms would face collision probability that makes current orbital debris concerns look trivial. Launch windows would need to be calculated to thread through gaps in the ring. Heavier shielding would increase payload mass and reduce what you can actually put in space. Failure rates would climb. Maintenance would become nearly impossible. GPS would degrade. Global telecommunications would become unreliable. Weather prediction, which relies on satellites for storm tracking, cloud imaging, sea temperature monitoring, would take a major step backward. Shipping and aviation, which depend on accurate GPS, would operate with wider error margins and higher fuel costs. The global economy runs on invisible infrastructure. Most of that infrastructure is in orbit. A ring would be at war with it. And then there's the shadow. The same seasonal dimming effect that may have triggered the Hernantian glaciation would begin playing out again. Cooler winters in whichever hemisphere faces the ring's shadow. Colder equatorial regions during equinoxes. Subtle but compounding changes to ocean circulation, storm patterns, growing seasons. A degree or two of cooling sounds modest, but remember, the last ice age was triggered by roughly that much change, sustained over long enough timescales. We live in a world where 1.5 degrees of warming is considered a crisis threshold. A ring-induced cooling of the tropics wouldn't necessarily cause an ice age within human memory, but it would be felt. In crop yields, in monsoon patterns, in sea ice extent, in the way storms form and move. Finally, the ring would scatter light across the night sky at every wavelength. Ground-based optical telescopes would struggle against the background glow. Radio telescopes near the equator would face constant interference from ring material. Any signal sent to or received from a spacecraft on the far side of the ring would carry noise. We would gain the most spectacular sky human civilization has ever seen, and we would lose the ability to properly study anything beyond it. Let's be honest about where the science actually stands. The ring hypothesis is not proven. It is a compelling, physically coherent, statistically well-supported working hypothesis. There is a difference. Here is what the evidence currently shows. A 40 million year spike in L-chondrite material in Ordovician sediments, enriched 101,000 times above background. 21 impact craters from that period that, after tectonic reconstruction, all fall within plus 30 degrees of the Ordovician equator, a statistical case that this distribution is a 1 in 25 million coincidence if impacts were truly random. No matching spike on Mars or the Moon, ruling out a standard asteroid belt breakup, a physically plausible mechanism. Roche limit tidal disruption, Hill sphere capture, collisional damping, equatorial ring 40 million year decay. A predicted ring lifetime that matches the observed geological duration of the anomaly against this. The main counter-argument is preservation bias. The idea that equatorial tropical regions simply preserve craters better, and that there may be high-latitude Ordovician craters that were eroded or subducted and no longer exist. That is a real concern, and it is why this is still a hypothesis rather than a consensus. The ways to test it are clear. Find more Ordovician craters from the right period. If they keep falling near the reconstructed equator, the hypothesis strengthens. If we find confirmed ones far from the equator, it's in serious trouble. Refine crater dating using higher precision techniques to confirm which craters truly fall within the L-chondrite spike timeline. Run tighter simulations of near-miss tidal breakup events to calculate what percentage of debris from a 10 km asteroid would actually be captured in Earth's orbit versus escaping. Compare composition across Ordovician impact sites to confirm they share the same L-chondrite fingerprint, the same parent body broken apart in the same event. The answers are coming, they are years away. They require drilling, isotope analysis, crater fieldwork across multiple continents, and refined computational modeling. But one thing Tompkins says with confidence is worth sitting with. This wasn't the first time Earth had a ring, and it won't be the last, most likely. The Roche limit is not going anywhere. The asteroid population is not diminishing. Near-miss events are a statistical certainty over geological timescales. At some point, whether in 10 million years or 100 million or a billion, another large rocky body will pass too close, and the sky over Earth will change again. You started this video looking up at a sky that felt wrong. Now you know why it once was, and why it may be again. Let's close every loop. We stood under the ring, a pale, dusty, rocky arc cutting the sky from horizon to horizon. Not Saturn's glittering ice. Earth's ancient stone, silent, massive, permanent twilight in the mid-latitudes. We found the anomaly, a 40 million year global spike in L-chondrite material starting at 466 million years ago, enriched 100 to 1,000 times above background, embedded in limestone from every continent on Earth. We reconstructed the craters, 21 Ordovician impact sites, traced back through 466 million years of plate tectonics, falling within 30 degrees of the ancient equator. 1 in 25 million odds if they were random. We eliminated the asteroid belt, because Mars and the Moon show no matching spike, and any debris from a belt collision would have hit them too. We built the ring, a 10 km asteroid, a near miss inside the Roche limit, tidal disruption, Hill sphere capture, collisional damping, equatorial bulge alignment, and a locked ring system inside the Roche limit where moons cannot form. We watched it fall for 40 million years. Orbital decay, exospheric drag, solar wind erosion, lunar resonance, constant rain of equatorial impacts, exactly matching the geological record. We connected it to extinction, a seasonal equatorial shadow dimming tropical latitudes, cooling winters at the poles, helping push Gondwana into the Hernantian glaciation, triggering the second largest mass extinction in Earth's history. 85% of marine species gone. We imagined it today. Ringed skies at dusk, permanent ring shine, satellite infrastructure under siege, communications degraded, subtle climate shifts, ground-based astronomy compromised, wonder and catastrophe wearing the same face. And we left the hypothesis honest, not proven but compelling, built on physical mechanics, geological evidence, statistical argument, and a planetary solar system pattern we can see repeating at Mars in real time. The next test craters are still in the ground somewhere, in limestone beds not yet drilled, in ancient Ordovician rock on the floor of oceans that haven't been properly surveyed, in drill cores that haven't yet been pulled, in tectonic reconstructions not yet refined. The ring is waiting to be confirmed or overturned. Science is always this, a story in progress, with better chapters still being written. But here is what I keep coming back to. The night sky you look at tonight, empty, familiar, dark between the stars, is not the permanent condition of this planet. It is one phase in an incredibly long story. For hundreds of millions of years, it was just ocean and embryonic life. For 40 million years, it may have glowed with a stone halo that no creature with eyes had evolved yet to see. For the last few 100,000 years, we have been the first beings on this planet capable of looking up and asking, what is this sky, and where did it come from? And it turns out the answer is, it was built, it changed, and it will change again. One day, on a future Tuesday evening nobody alive today will see, someone will step outside, look up at a sky that feels wrong, and see a pale stone river cutting the heavens in half. And they will know what happened, because we will have told them. That's what science is, not just understanding the present, inheriting the past and leaving instructions for the future. Earth without rings feels normal to us, but in the full lifespan of a planet, this might just be the in-between. Thanks for watching. See you in the next one.